Okay, so we're ready to start. Good afternoon, everyone here in the room, and also to the folks that are online with us today. We'll go ahead and get started. This is the session on the art of troubleshooting that was in your agenda papers. Quick introduction. My name is John Piddle. I am the CTO for Riverbed US Federal. I've been practicing performance engineering since the 1980s, very involved in protocol analysis since 91, and started with OpNet and Riverbed back in 2005 in professional services. So I've been working with literally hundreds of customers over those years, hundreds of troubleshooting engagements, deploying visibility products that help you detect and resolve problems. So a lot of what we're going to talk about today is based on that experience. I love the mystery of a complicated problem. Simple problems, usually other people will handle. They'll come to me when something's been lingering for many, many days or weeks and there's no obvious answer, so they may reach out. I shaved off my beard in 2003, just a little fun fact, and you can see my email address there. Please feel free after the event to email me at any time. I'd love to interact with the folks here in the session, both in person and online. So today's topics are around troubleshooting, and we're going to start with, the main thrust is, why does troubleshooting take so long? A lot of people say, why, geez, it shouldn't take so long. Why does it take so long? And we're going to be drilling into that in today's session. First, we're going to look at, is troubleshooting an art? Some people would say it's an art. Some people would say, no, it's a science. At the end of the day, it's all about reducing time to troubleshoot and restore service. I'm going to walk you through a troubleshooting process taxonomy that I put together to help create kind of a common language and framework for troubleshooting. And then I'm going to share with you a real-life NPM, Network Performance Management troubleshooting exercise that I did with a customer a few years back, and they were kind enough to let me use that as a case study because there were so many interesting things that we found, as long as I anonymized all the material. So we're going to do that, and then we'll do a wrap-up. So troubleshooting, is it an art or a science? I brought a couple of friends with me to help in that discussion. The first you might recognize, his name is Bob Ross. He's a famous artist from the US. One of his most famous quotes is, when you make a mistake in your painting, no problem, just turn it into birds. So as we go through troubleshooting and we find some unexpected things, we're going to twist and turn and make our own little birds, if you will. And then my other friend to help me in the discussion today, you might recognize from Back to the Future. It's Doc Emmett. He invented time travel. So how much more of a scientist could he be? And he's going to be helping us out a little bit today. So quick compare and contrast, is troubleshooting an art? Well, the artful aspect tends to be, we would tend to be very reactive in our troubleshooting. It's highly individualized. The way I do it is my way. The way you do it may be your way. Somebody else does it their way. Not really any consistency. And of course, very experience-based with the tools that we feel most comfortable with. We might be reluctant to get outside of our comfort zone, even if there's a better tool that provides better visibility or better analytics. We might be highly adaptive. You hit a brick wall and you say, well, I've got to try something different. Okay, what might I do? And you might come up with an adaptation to whatever it is that you're troubleshooting. It's not typically repeatable. So if you were to ask me in the old days, if I was troubleshooting something similar from a year ago, I may do it a completely different way, just because of how I was feeling that day. As compared to a scientific approach, where a proactive mindset is built in. If I'm going to be proactive, I have to plan what telemetry do I need, where do I need it, how much do I need, what kind of alerts do I need, et cetera. And we're going to be talking a little bit about that coming up. A repeatable process based on collective experience. Hopefully we're combining experience from several different people into a common troubleshooting methodology that we all benefit from. We would engineer visibility into the environment in a very purposeful way, not adding tools after the fact, but thinking ahead of time, what tools do I need to support what types of technologies and what types of applications. We would pre-plan relevant dashboards, alerts, and triage and troubleshooting process so they're at the ready when we need them. Highly leveraging templates so we don't have to reinvent the wheel continuously. And with a mindset of we really want to exercise continuous improvement at the end of the day. So that's just a little compare and contrast. So you may have heard management ask this. Maybe you're working in a war room and management comes in for the hourly update. Why is this taking so long? Why don't we have an answer? What the heck is going on? Why can't we figure this out? Well, I think it comes down at a high level to two particular things. The first is complexity. I mean, we're dealing with an insane amount of complexity compared to, and I'll date myself a little bit, compared to the IBM mainframe days, where you had one compute platform, you had one vendor for storage, you had one vendor for communications. There was some downsides to that, but from a troubleshooting perspective, there was a lot of upside to that too. So in today's world, we've got different servers, different hosting options. Servers are in various locations. They might work in a distributed or work in tandem across different locations. Your users could be in any number of locations. For DoD, that's not so much the case, but in the commercial world, users can be in coffee shops, they can be home, they could be in a branch office, you never really know where they are. And then with new security protocols, that adds a new layer of complexity to how we get visibility and how we do troubleshooting. Probably zero trust is something that you guys have started to hear about or have been hearing about quite a bit. That adds quite a significant layer of new complexity. And just thinking about troubleshooting, most organizations may have some kind of document, looks something like this, somewhere in the organization that might be up to date. Chances are it's not up to date. You know, it was an effort at one point to say, we have to document our process, right? Let's get it done. And some of these, you know, truly reflect the complexity of the environment. The other reason why troubleshooting takes so long, and this is not really pleasant to say, but it is kind of a hard truth, it's really a lack of preparation. A lot of times new applications get deployed in the environment, we don't even know it until somebody says, oh, we have to go troubleshoot application X, and we say, what's that? Where did that come from? Who installed that? Where is it running? What are the IP addresses? How do we monitor it? Even for the things that make it through a discipline change management process, there's some organizations where they just don't think about performance engineering as part of what needs to be happening. So a lack of preparation. We're going to talk through some preparation items and ideas in today's session. The first of those is something I call IT service onboarding. I've shared this with various customers. They pick a different name for it. They might call it service enrollment, for example. I had one customer said, that's what we're going to call it. It's like, no problem. Whatever you want to call it is fine. And in essence, you're trying to prepare yourself in advance, all with the goal of reducing the time to do troubleshooting and to make sure you also have metrics for SLA and KPI reporting as well. So let's take a look at what IT service onboarding is all about. So first, it positions you to be proactive. That's one of our first kind of scientific principles. We want to be proactive. We want to be proactive. We're going to configure visibility, alerting, and troubleshooting process aligned with the application that we're targeting. So a separate set of those things specifically for the service that we will need to care about. Built-in alignment with the service architecture and deployment of that application/IT service. And then the other kind of key part is giving the support teams a chance to weigh in and say, I'm ready. I understand the dashboards. I understand the alerts. I understand where the monitoring is. I understand how much visibility there is. I understand the troubleshooting process that was created. So they get a chance to say up or down, go to production, don't go to production. There's some customers that are very rigorous about that, and other customers that say, yeah, we're not going to deal with that right now. We're just going into production. Something about damn the torpedoes, full steam ahead. That's a military joke, right? Okay. All right. With the onboarding process, there's 4 categories of what I like to call monitoring assets that you're going to create. And I really use that term on purpose because I think of them as business assets, just like other assets in the business that contribute to the success of the business. So they're grouped by IT service, kind of service-related collateral, and I'll walk through those in a minute, instrumentation, visibility, and different process and workflows. So in the service collateral group, the first thing we want to do is find out, do we have any documentation about the architecture for this application? Do we know what it's supposed to do, what it's supposed to talk to? What are the different application tiers? And where are they deployed in the environment? And usually when I walk into a customer's environment and we have that discussion, the answer typically 99% of the time is, oh yeah, we have architecture drawings, but they've never been updated in the last 3 years. So we're not really sure, but no problem because we can use our instrumentation to kind of validate what's really happening on the ground in the system. And then what are the various business use cases? What can we learn about when users are online? What are the critical transactions? What happens? What does it mean to the business if they're down for 5 minutes or 10 minutes? Is it all transactions are critical or just some, all work groups or just some, et cetera? Some kind of context about the business impact of the application. And then in terms of instrumentation, we would call out, well, what are the detailed performance metrics for both the application and the network in the context of this IT service that we're onboarding? What threshold alerts should we have? What are the KPIs that we have to support for service reporting? And can I even provide that data? Do I have enough telemetry to know about throughput rates and transaction rates and up down time and availability, et cetera? And then in terms of visibility, creating some very custom dashboard views for that application. So let's say the application is called payroll. I think we would all agree payroll is pretty important. There would be a dashboard specifically for payroll where you could see all the relevant telemetry and performance and availability data across all the different technology stacks associated with payroll. So network metrics, server metrics, application, end user experience, et cetera. Daily performance reports, something that gets scheduled every day for the previous 24 hours that sits in an archive so that you can know what does normal look like. Very important. That's one of the hardest questions. What does normal look like? Different trending reports as well as network and infrastructure dependency maps are important. And then coming back to the troubleshooting topic, how would we troubleshoot this application? If you get alert 10, I'll just make that up, something called alert 10, what do we do next? How do we troubleshoot that? Where do we look? What data do we use, et cetera, et cetera. And then a root cause analysis template. Change management is interesting in this context because there's a lot of change review boards or CABs, change advisory boards, where if you go to them proposing a change, they're going to want to know what is your back out plan? What is your criteria pass-fail for knowing do I even back out or not? And most of the times the people who prepare that material don't know what normal looks like in production, so they come up with sort of a vague back out plan that's not really effective for what you're trying to accomplish. So change management is important. And then ensuring that we're plugged in and relevant and following any continuous improvement process that's in the organization. So this is the very high level view of IT service onboarding. These 2 or 3 slides come from a deck of about 45 slides where we go into a lot more detail. Wasn't time today. It's something we can do post-event. Happy to do it. I want to move on now and talk about a taxonomy that I call performance troubleshooting taxonomy. The goal is to create a common language and foster collaboration between teams. Something that we can share amongst network team, server team, application team, help desk, service desk, security, virtualization, cloud team. Let's all get on the same page about how we troubleshoot, how we refer to those troubleshooting activities. It starts with a list of symptoms and conditions in this taxonomy. We're going to call out symptoms are those things that a user might say when they call the help desk. What would they report as a symptom? Whereas a condition might be something that one of the monitoring tools detects in the environment and raises your attention to that condition that now you need to take some further action based on that condition. So these are kind of the triggering events, symptoms and conditions. Those typically, well, they always have causes, don't they? Sometimes the cause might go away before you figure it out. Everything returns to normal and we don't know why this thing happened. But they do have causes. You learn about those causes through investigations. Those investigations are performed by one or more teams. And those teams are going to drill down into different devices and domains, basically their subject area of expertise, and they're going to use a variety of different tools and data as part of that investigation process. So I just have a couple of screenshots here. There's an Excel spreadsheet that we have available to share. All of this stuff, the whole idea of being here today and presenting this material is sharing. What I've seen work, what I've seen not work, being collaborative, everything we hear, everything that we're talking about today, we can have a follow-on discussion about. But this spreadsheet will be available for distribution. So there's different tabs. There's a tab for symptoms. There's a tab for conditions. And you can kind of see there's just a inventory list of, did that come out better? I know it's hard for the people in the back. This is what the users might report in when they call the help desk, if they call the help desk. There's kind of anecdotal evidence that people won't call the help desk right away. They think, oh, somebody's probably working on this. I'll wait and call. Maybe I'll go to lunch or I'll get a cup of coffee if it's still happening. Then I'll call. Nobody loves to call anybody here love to call the help desk? It's like, yeah, no, I don't want to be unkind. The help desk people work really hard. Okay, and then over here, different conditions that your tooling might pick up. What are the different causes? Well, I've cataloged 25. There could be more, certainly, or some of these could overlap. But these are typically at a high level what might cause a symptom or a condition. These are the types of investigations that you may do depending on where you might have to look, looking at circuits, looking at servers, looking at the applications, looking at Wi-Fi. It's a pretty healthy list of 29 items. And then where might you have to look? In the end user space, in the server space, in the application space. The service provider who's providing you circuits. So we've come up with 33 of those areas that may need attention. Some might be like on the right-hand side, call manager and PBX and SIP. That's really for specialized applications like unified communications. But some of these apply to everything like investigating the firewall. And then what types of tools might you need to use? Well, monitoring on the end user device, maybe SNMP polling, NetFlow. Hopefully the folks in the room are familiar with NetFlow and packet analysis, etc. So after having stepped through that a little bit and thinking about the question when your manager asks, why does troubleshooting take so long? The answer is because there's in the ballpark of 60 different things that you might have to go troubleshoot. there could be 25 different types of causes, root causes, if you will, that you have to figure out which one. There's 29 different investigations, and that's just on a list that I prepared. I was on a flight, I was frustrated, I was trying to get this stuff out of my head and just started typing. You could have 5 to 10 different teams that have to work together to try to troubleshoot an issue and share information and be collaborative. And then, of course, 32 different domains and 13 different types of tools and data. So why does it take so long for troubleshooting? Because it's a hard problem to solve. So if you took that taxonomy and you kind of assembled things into a workflow, there's some simple things that, and this is a very abstract picture, just saying, hey, linking certain things together. I've got this symptom. What investigation would I typically do? Where would I typically look? What would I be looking for? Stringing that together might look like this picture. When the situation is more complicated, there may be some decision making along the way, and you may have to drop off into different threads of investigation and look in different areas. And really part of the key here when I put this taxonomy together is to hopefully get different teams all on the same page about how do we approach troubleshooting in our organization, and how can we have some consistency in the way we use certain words and what they mean. Ultimately, at the end of the day, you want to be positioning for automation to do those investigations for you. But you have to really understand what the manual process is first. If you start with just automating without knowing what it is you're automating, it's going to be hard to envision success from that, because automation should really be taking manual steps and making the computer do the work. So, quick review. Is troubleshooting art or a science? So we really stepped through a couple of quasi-scientific or objective details, if you will, around troubleshooting. We looked at the onboarding process, we looked at the taxonomy, we saw how complex things were. We saw that we could kind of create building blocks of different investigations that look at certain types of data that we tie to certain types of symptoms. That would be kind of the scientific area of this, right? We're really trying to create a structured, repeatable process. So having that as a background, let's dive into our customer example that they were so gracious to let me share. I have to let you know in advance, this is not going to be pretty. Anybody who's done troubleshooting will appreciate what this means. So just a spoiler alert, some of the stuff we're going to find. Lots of visibility gaps. I'm trying to troubleshoot stuff I can't see. There was no app onboarding, no service onboarding, no dashboards, no alerting, nothing was created. And there were quite a few different network path surprises. So this customer was an early adopter of SD-WAN, and there were quite a few surprises about where traffic was moving at any given point in time. So the data that we used and the tooling that we used for this exercise, these are Riverbed Products Net Profiler, which is our flow collection, analytics, and reporting. App Response, which is our real-time packet-based performance monitoring, analytics, and capture. There's some offline tools for doing fast and focused performance analysis of very large PCAP files, that's Packet Analyzer Plus, and then Transaction Analyzer to do some advanced performance analytics of a PCAP, and even a little bit of modeling and simulation for transactions. So those are the 4 tools. There might have been some Wireshark used as well. I'm a big fan of Wireshark. I teach Wireshark classes. There may have been some Wireshark as well. So let's look at the reported symptoms. So there were file transfers from Bangalore to US West Data Center that take, how long did it take? It takes forever. Ask the user, how long did it take? Oh my God, it took forever. It's unacceptable. You have to fix it. The network is the problem. The problem's been occurring for weeks and no one could figure it out. Those are the problems I like. happy to say. And it's been impacting productivity. People are working extra hours and causing missed deadlines. This happens to be a software engineering team. They're trying to get to the code repository, bring it down to Bangalore so they can work on it. They're missing their development deadlines because of these problems. So really a messy problem. You wouldn't think it would be so impactful. It's like, it's just a slow file transfer. But it was actually quite impactful to this particular team. So thinking to the taxonomy, putting together an investigation plan based on the symptoms reported, we'd probably do the things that you see here. Let's confirm date, time, what was the network health at that time, what was the client health. We may need to look at some TCP details, like what TCP options are being used by looking at packets. Maybe examine what the expected network path was, and even kind of predict how fast could it have been. In a perfect world, how long should it have taken? And there's some back of the napkin math you can do, and one of the tools has some simulation for that. But this is what we actually did. We did the stuff we planned, and then we started finding all kinds of crazy things, and we had to pivot in different directions. And I'm going to step you through all of these things that we found, kind of in the order that we found them. It's like the poster child of what you don't want to have happen when you're troubleshooting. First off, the good news was we had very objective information from the user about the nature of the file transfer. What time of day, what day, how long did it last, what was the average megabits per second as measured from the client side. And this was just a wget script, which is basically a script that gets a HTTP object. So that was very, very useful. A lot of times you don't have this clarity. People will say, I think it was last Tuesday somewhere in the afternoon after tea time. It's like, okay, I can't help you. I need better. So this was great that we had that. In terms of the expected network topology, and this of course is a simplified view, on the data center side there was two ISPs, internet links 1 gig each, BGP connected to the ISP. Bangalore there was two ISPs, also internet connected BGP at 100 meg. And latency was around 260 milliseconds. So this is fairly typical for international at that time, at the physical network stuff. There was actually SD-WAN routing going on in there, but this is the simplified view. So our first kind of telemetry that we're looking at is from our packet-based appliance, app response. And there was an app response in Bangalore and another app response in the data center, so we could see performance on both sides of the link. And I'm going to try to use my magic magnifier here to show you a couple things. The blue line is network throughput based on the packet arrival rate into the appliance. And this appliance gets a copy. It's a passive appliance. It gets a copy of the traffic through a network tap or span. So the blue line was throughput megabits per second. The yellow line is retransmission count. How many retransmitted packets did we detect during the life of this transfer? And the answer to that is sort of good news in a way. There's no retransmissions. So it's good news there's no retransmissions. The bad news is it's not retransmissions. We got to figure it out. If it was retransmissions, that would kind of take us down a different path. So in order to really kind of understand why this is not happening faster, we really need to look at the packets. We got to look at the TCP options. We have to see, do they have selective acknowledgement, window scaling, maybe some other options that MSS size that might clue us into why didn't it go faster? Because it could have gone faster. So let's drill into, we're going to use the Bangalore app response appliance. It's great, right mouse click, say download the packets of interest. And it was all good until we found this. And it was the first preparation issue that we found. There were no packets on the appliance. The performance data, the metadata was in the performance database, but there was no packets. Why not? Because the capture job had never been set up. Why not? Because the network engineer started and then he got distracted and he got busy and he forgot and he never went back and he never configured it and nobody checked. And there was no process like a deployment checklist that anyone has to fill out and sign off, etc. No problem, because we have an app response on the other side that in the data center that would have seen the same packets. Good, let's go look in the data center. Well, we've got another problem. In the data center, we don't seem to see this traffic. Now that's weird because that appliance is supposed to see all traffic, but it didn't see this traffic. It's like, okay, that's a head scratcher. So I've got a road sign that you might see as you're driving along, like danger, warning, look out, etc. So this is really quite unexpected. The Bangalore app response sees the traffic, but the data center AR does not. So we have something more wrong than just a slow file transfer. We have an inability to do troubleshooting, to work in the environment and be successful. So we're going to pivot away from packets over to flows, and we're going to take a look at the Net Profiler product is a flow collector and analytics tool, and it's receiving flow from all devices, switches, routers, firewalls, etc. So we're not relying just on packets. We should see all of these transfers from a flow perspective. And the one that we care about in particular, we should be able to see. So let's take a look at that. So there's a report in Profiler, which is very handy, called the Flow Log Report. This tells us every interface that saw this particular TCP connection. So it gives us a sense of where did it go through and where did it not go through? What interfaces did it pass through? Which interfaces did it not pass through? That's what I meant to say. So it's really valuable. So at the front of the flow log, there's an overall traffic summary report, and you can kind of see that there might have been a couple of transfer attempts during this window of time, like this is probably one transfer, that's probably one transfer. I don't know about over here, maybe this is one and then something happened here, it doesn't look too healthy, something doesn't quite look right. But the good news is there's things we can see. And if we follow down to, well, let me just comment. These spikes, they don't look quite right. It's like, why would there be any of these spikes? They're kind of they're outliers. They don't look quite right. So if we scroll down into the flow log section of the report, I just want to give you some very quick orientation. We're looking at different rows here, like the white row, the gray row, the white row, the gray. Each one of these rows is a different TCP connection. So there's statistics for each connection, and there's also over here a list of interfaces that we saw in the client to server direction. I believe that's what that says. And then in the server to client direction, because NetFlow is directional. So you have to assemble NetFlow records to get like a complete connection. So I had to redact this, of course, but we're going to zoom into two of those rows and make an assessment. So we're now looking at two connections. The top row is one TCP connection. The bottom row is a different TCP connection, but it's the same client, it's the same server. This is a filtered report. So what's really baffling here is for a given TCP connection, I have 8 interfaces reporting client to server direction, and I have 10 interfaces reporting in the server to client direction. It's like, so we call that asymmetric routing, asymmetric switching. Why do we have that on our network? Is that expected? Is that good? Could that explain why the data center app response didn't see the connection we were looking for? But equally baffling is a subsequent connection, which is in the gray row in the bottom there, used a different path than the top connection. Now we have 9 interfaces, client to server, and fewer interfaces in the server to client direction. Instead of 10, we now have 7. So this is what I would describe as an unstable, unpredictable, unsupportable network. Just to put a fine point on it. And we got to figure this out. So now I have a new traffic sign on the sign, because this is really bad. This is really, really bad. So different transfer attempts are using different paths. The paths are different in each direction. it needs more research. They seem to have different performance profiles. Some paths seem to get more megabits per second than other paths. Why is that? And so what we're going to do next is we're going to look at a different net profiler report grouped by network interface. Again, it's the same two IPs, it's the same time frame. And now we get a little different view of which interfaces are reporting and what level of utilization does each interface have. So for example, I'm going to go over here to this one in particular. This looks fairly consistent and fairly normal across all interfaces, right? The colors overlap except for the purple. Something about that purple we need to talk about. So purple is one of the firewall interfaces. So it's the firewall that's generating flow data that feels unbelievable. It's like, I can't trust that data. There's something wrong with it. In this other transfer, we had a spike. We got pretty decent bandwidth, and then we backed off on actually a whole bunch of interfaces. So that's kind of interesting. Over here, we never got above 10 meg. And then over here, again, I don't know what these little transfers are, but we never got above 10 meg over here either. So now we've got kind of an additional perspective that, okay, there's something wrong with the firewall flow data that probably needs some attention. So I'm kind of keeping this updated as we go along. So firewall purple is reporting values that can't be right. We found a variety of visibility and network routing issues that need attention, but what about our actual file transfer? We haven't even gotten to that yet, right? We haven't even gotten to that. So we're going to pivot again. And being a curious person, which I am, I thought, okay, well, we can't see the one transfer that we were originally started with. We didn't have packets for it. But Profiler sees all the transfers. Maybe there's one that might happen to be in the data center app response. Maybe we'll get lucky. So I happened to find this one that ran for 26 minutes and 9 seconds. So this one connection for a file transfer on port 80, again, between the same client and the server. Remember, the one we were given was like 13 minutes or something. That took forever. Well, here's one that took twice that long, 26 minutes. And what's really interesting about this and looking at the data is we start to generate some throughput here, but then we back off, and then we flatline. Zero throughput for the pretty much most all of the connection. Zero throughput. The connection is alive, but there's no data going across it. It's like, holy cow, what could that be? So to figure that out, we need the packets. Good news. Right mouse click, go get the packets. In this particular case, we are filtering down to one connection, two specific IPs, specific client port, server port. So when I pull those packets down, it was about 10 megs worth of packets, put it into the offline analysis tool. There's a feature called App Doctor, which I use all the time, which tells you where the delay is occurring. Do I have a server issue? Do I have an application issue? Do I have a protocol issue? Do I have a network issue? So the big purple blob is a protocol issue. Something's happening with TCP. If I double click on that blob, I get a list of the 3 metrics that are most relevant to the blob. Those 3 metrics are in-flight bytes, that's the top chart, what Wireshark might call bytes in flight, we just call it in-flight bytes, retransmissions, and advertised receive window size. And notice that advertised receive window size drops to 0. If you've worked with TCP and Wireshark and other tools, you know that that's called a frozen window, where the receiver basically says, I have no more space, no more buffers, don't send me any more data. So is this a network issue for this connection, or is it something else? This is a client-side issue where the client says, stop sending data, I have no place to put it. So the network guys are trying to fix this. They wouldn't, at the time, I don't think they knew what a frozen window was, so this was a useful exercise. Some summary statistics, yes, there were some retransmissions, not enough, I think, to be too interesting over internet. But the frozen window number, which is here, 1,443 seconds, that's the root cause for this particular transfer. So we can visualize this capture in a couple different ways that's useful. In this visual, we're combining some different views to look at all at once. We can see advertise receive window at the top. We can see something called data exchange chart, which is basically a bounce chart showing packets moving over time between the two hosts. And depending on what we click on in the middle chart, we'll get summary decodes like you're used to seeing in Wireshark. And what we did here on this screenshot is, it's kind of hard to see, but there's little black dots here. These 3 lines I've selected with the mouse, and these packets showed up in the summary, and sure enough, you can see the client is reporting a window of 0. So just kind of validation of what the other charts were already telling us. So quick recap, we've got unexpected network paths, client-side frozen window, we've got retransmission gaps in visibility, unexpected metrics from firewall. Whew. Boy. By the way, this didn't happen like after lunch. This took a couple of days to try to get all together. But let's look at those retransmissions a little bit more. So we're going to look at the packet decode summaries for the connection. And it's probably hard to see from the back of the room, but here's our get from the client. Get me this blob of whatever. Server says okay and starts to push out a bunch of payload. But none of that payload ever makes it to the client. Instead, what happens from this view, now we start seeing, here's the OK message again and a bunch of continuations, but now the packet sizes are smaller. The packet sizes are smaller. So they made it through the network because they're being acknowledged down here, but something made the server decide to reduce the packet size. And we need to talk about what is that all about? So the first burst of segments gets retransmitted. What could cause this? There must, underline must, be a network device somewhere dropping the packets and hopefully telling the server why via the ICMP protocol. So ICMP is really important in the network, Internet Control Message Protocol. There's lots of different types of records we're going to, or flavors of ICMP messages. We're going to see those in a second. But we don't see any in this trace. Why don't we see them? And the answer is because we heavily filtered this trace to just one connection between 2 IPs on port 80, because that was our focus. So what we need to do is we need to go back to our appliance, and we need to change our filter. We're going to download all packets from and to the server because we don't know where this suspected ICMP packet is coming from. So we're going to change our filter to say everything from and to the server. So that turned out to be a 4 gig file for the time period of interest. I love Wireshark, but I don't love opening 4 gig files in Wireshark. So Packet Analyzer Plus is an offline tool that eats very large PCAPs and lets you run very quick reports. This particular report is a canned report called ICMP types over time. So this is essentially saying, hey, in your 4 gig PCAP, there's some ICMP that occurred, let's say, around this time frame here. And oh, by the way, those are all destination unreachable. That's kind of what I expect to see. So let's download, let's not analyze the 4 gigs. Let's analyze just the ICMP messages. So the good news is you right mouse click on the chart, the brown line. You say send those packets to transaction analyzer, and now we have a filtered small list of about maybe 15 or so packets that we have to focus on. So all that filtering, all that noise, right mouse click, it's gone. So this is what we needed to see. So here's our ICMP type 3 code 4, which says, hey, destination unreachable, why? Fragmentation needed. The biggest packet this particular router would accept is configured for 1192. The original packet was 1332. So the router dropped it, informed the server, as long as the firewalls in the network allow these messages through. So if you guys are network engineers and you do network troubleshooting and the security team says I got to turn off all ICMP, because because we have to, you got to say, please don't turn it all off. There's some that we need, like this one is really important. Okay, so now we have more information, unexpected network paths. Now we know MTU sizes are not what we thought they would be. We've still got that frozen window, retransmission gaps, and visibility. There's one more detail before we wrap up, and I think we're almost out of time. And we're almost done. The initial receive window, when I looked at it, I thought, geez, for that level of latency, really should be bigger. So there's something called bandwidth delay product, which is a calculation you can use to figure out optimal receive window sizes given certain network conditions. So our tool does that automatically. You can also go to speedguide.net, bdp.php, and you basically plug in the link speed and the latency, and it gives you the optimal receive window, which is 2.77. So let's recap. We found all these things. Marcus hasn't given me the 10-minute signal yet, so I think I'm okay. All right, okay. We've talked about all of these, this crazy dynamic routing, MTU, receive window too low. Lots of stuff here. Like why does troubleshooting take so long? Because sometimes there's a bunch of stuff that's broke, and it might look similar, but it's not similar, right? So sometimes when you're troubleshooting for somebody, you never hear back from them, right? And when you don't hear back, you kind of figure, well, I guess they're not complaining anymore. They must be happy. This guy was nice enough to say, hey, here's a quick update, sir. I didn't let you know sooner, but the MTU inconsistencies fixed on the whatever gateway. For some reason, this particular device, again, SD-WAN, the VPN tunnels, were misconfigured. Instead of 1332, somebody made a typing error, and it was 1132. So a simple, common typing error, weeks worth of confusion, weeks worth of frustration, thank you, weeks worth of missed deadlines. And the good news is now when they are doing a transfer, they get 100 meg. They fill up the pipe. So that's really good news, right? Mission accomplished. And what he told me was that ICMP fragmentation needed was the silver bullet to explain what he had to do next. So again, when you're security, if anybody's here from security, I love security. Let's get that out in the open. But turning off all ICMP it creates huge challenges for trying to troubleshoot the network. Some ICMP, yes, you do need to. Good news is firewalls can be selective about what message types they drop and which they don't. Okay, so performance troubleshooting, is it an art? Is it a science? And what I believe it has to be a little bit of both. If it's all one, it's just not going to get better over time. It's got to be a little of both. So if it's all art, it'll never keep improving. If it's all science, you can't pivot. So I believe in my point of view is it should be a little bit of both. So there's a sample investigation log that I was prototyping with a team. We're not going to have time to look at that now, but just think of a Word document where everyone can collaboratively paste screenshots of the things that they're investigating. And there's hyperlinks in the Word document or Confluence. It can be a Confluence page. Anything that's easy to navigate, so you've got a table of contents, it's easy to jump around into very specific content. And maybe there's even executive summary. On this date, we found this. Here's what our hypothesis. Now we're going to investigate X, and just a living log of what people did collectively to troubleshoot. So recommended next steps after, not immediately after this session, but shortly after. Learn more about IT service onboarding from your Riverbed team. Here in APJ, there's a very robust team. They're fantastic. Download and evaluate the troubleshooting taxonomy spreadsheet. I'm not exactly, stay tuned on where that'll be. I'm not sure how we do that with the conference, but we'll figure it out. And I think they know who's here, maybe, and we'll figure it out. Evaluate your current performance troubleshooting stance against today's material and adjust where appropriate. Take what you need and leave the rest. If you like something that you've heard, try it out, see if it makes sense. If you don't use it. And if it's allowed, please email me and share any anecdotal results of how this material may have helped you in your work, because I'd love to just get a sense for, is it helping? And then come by our booth this week. We're up in F11, F13 on the ground floor. We'd love to talk to you and maybe show you some demos and talk about your more difficult troubleshooting activities and maybe some ideas on how it could be done faster. Some additional resources, also known as a shameless plug. I mentioned I'm a Wireshark instructor. I've got several classes recorded on SharkFest YouTube channel, so feel free to take a look at those. There's so much good content. I mean, honestly, so many contributors, so much good content. Chris Greer, Saki Block, and I've got some of my favorites here. I'm on LinkedIn. Feel free to connect and feel free to email me at any time. And I think there's a few minutes for questions, Q&A.